Hello and welcome everyone to another session in the DataHour series. We are thrilled to be here with you for a session full of action-packed learning. I am Rushikesh Daigude, part of the data science team at Analytics Vidhya. For those who have joined us for the first time, let me give a quick brief introduction to the DataHour sessions. The DataHour is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It is a fun way to understand the concepts of data science from leading players in the data tech domain. And as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value addition for our community members. Now on to our session today, which is on when Airflow meets Kubernetes and introduction to MLOps. The life cycle of a machine learning model is really complex. There are a number of phases starting from the exploration phase, which go up to deploying the model in production, and then further maintaining it. Each life cycle phase has its own set of hardware requirements, and even information from one phase needs to flow to other phases. In this DataHour, we have Anmol with us. He'll be explaining MLOps from the start, covering end-to-end operations of the ML models using the power of Airflow and Kubernetes. I hope you are excited to attend this DataHour with us. Before we kick things off, and I hand it over to our speaker, a quick recap of the housekeeping items. We are recording the session and will make the recording available in a few days on our YouTube channel. Please use the Q&A section for asking any question you might have during the session, and we'll be do our best to answer them as DataHour progresses or towards the end. Also, we'll share a poll about feedback of the session towards the end of session, which I request to kindly fill up. Now on to our speaker in the session of the DataHour, we have Anmol Krishnan Sachdeva with us, who is a hybrid cloud architect at Google. Let me give an introduction about him. Anmol Krishnan Sachdeva is an international tech speaker, a distinguished guest lecturer, a tech panelist, and has represented India at several reputed international hackathons. He is a deep learning researcher and has about 8 publications in different domains. He is an active conference organizer and previously has helped organize some of the most prestigious conferences like EuroPython, GeoPython, and Python Machine Learning Conference. He has done MSc in Advanced Computing from University of Bristol, United Kingdom, and currently works at Google as a hybrid cloud architect. In the past, Anmol has spoken at renowned conferences and tech forums like KubeCon, PyCon, EuroPython, and got invited as chief guest at various events. He likes innovating, keeping in touch with new technological trends, and mentoring people. So now over to you, Anmol. The virtual stage is all yours. Thank you.
Thanks a lot for the introduction. I hope my screen is visible.
Yes, you're visible.
Sure.
Great.
Yeah. All right. So so we are here to discuss about when Airflow meets Kubernetes, and it's quite an interesting topic. So we will be having 2 things addressed through this particular session. One will be we'll be having an introduction to MLOps done, and post that we will be getting into how we can leverage Airflow and Kubernetes platform for performing MLOps, right? So we will have this as an introductory session. We are not going to get into advanced details as such, okay? So it's beginner friendly session. Is the volume good now?
Yes, yeah, it's good.
Okay, sure. Okay, so I'll skip my introduction because already I've been introduced, so thanks. Just a disclaimer before we get started, the content and the views represented in this talk or session are my own, so these are not to be related to any of the organizations or companies I'm associated with, right? So the flow of the talk is as follows. First, we will have a look at what MLOps is essentially and why we require MLOps, right? What's the actual need of MLOps? We will try to get into understanding of orchestration frameworks and needs of orchestration. We'll get into the details of Airflow following that, and then we will have a look at Airflow on Kubernetes. That will be followed by a demo, and we will have towards the end a Q&A session. So let's get started with the understanding of why MLOps is needed, right? So essentially, the people who are there in the audience, you may be thinking that, okay, MLOps seems to be machine learning operationalization, or it has something to do with DevOps. You are right in that context. And the thing that you need to understand here, which many people uh, kind of skip or don't pay stress on, is that a production solution for machine learning requires much more than having a perfect ML code, right? You have things like configuration, you have data collection process, you have verification process, you have data serving deployment, you have the monitoring aspects, you have process management, you have analysis as one of the domains, you have feature extraction, and all of these things are essentially something which supports your ML model, which supports building of your ML model, which supports having a proper process for your machine learning pipelines, and also supports your models getting deployed in production, right? So generally, we see that when we are dealing with machine learning models, we tend to bring up some notebooks in Jupyter or maybe Colab, and ultimately, data scientists are the one who essentially deal with building the notebooks. But then we see that many of the notebooks don't go into production, right? So these notebooks are essentially not scalable. These notebooks are not replicatable, maybe, or reusable, or maybe we don't have reproducibility as one of the features. So it's very much restricted to the local environment of the data scientist who created the notebooks. And when it has to go to production, you essentially need someone else's help. And then is the place where data engineering person comes into picture, right? So you have this data engineer working along with your data scientist, and then you have essentially another person coming into picture, or another entity coming into picture, which is a machine learning engineer. So you have your data engineer solving your data ingestion related issues. You have your data scientist solving your data modeling specific issues, data preparation, feature engineering, data cleansing, algorithm specific issues. And then you have something called as machine learning engineer. That's another entity. That entity actually focuses on having your machine learning models deployed, served, and even kind of maintained going forward, right? So there are different stakeholders to this process, but we generally focus on data scientists or maybe one of these entities. So if we are from a platform background, we will be focusing on data engineering. If we are from data scientist background, we will be focusing on just data modeling. But all of these pieces have to be tied together. And all in all of these, when streamlined and put together in a fashion wherein we are receiving continuous feedback for the process that we are following for machine learning, gives us a good machine learning pipeline. And streamlining this machine learning pipeline according to standards and governance and compliance requirements gives us something called as machine learning operations, right? So we will get into that soon. But before that, let's understand further a few points which will help you. Yeah, the screen is shared. Is there any issue with the screen?
No, screen is visible.
Okay, great. Yeah, right. So we will touch on few more points before we get into the details of MLOps. Okay. So first thing to understand here is science is geared towards research, whereas engineering is geared towards production. Now, what this means is when you are talking about science, it's more about exploration. It's more about doing research. It's more about experimenting with the models, or maybe building models, having some iterations done, playing around with your data. And this is the role which the data scientist has to play. But that alone is not sufficient enough for your ML models to be served in production. That is where the engineering aspects of deploying, serving the model, maintaining it, and taking it forward, or maybe iterating on it, is something which is required. And that is where the machine learning engineers come into picture. Then we are striving for operational excellence. We don't need to kind of focus on just having these models built, but we need them to be aligned to our business needs. We need them to be regularly updating, right? So assume a scenario wherein you are a data scientist or maybe a machine learning engineer and you have been told to go about solving a problem for the next 6 months time, and you go and you start developing your model, you start prepping, you have done a lot of things. Yeah, I'll answer the questions towards the end, so please keep on having the questions shared on the chat. I'll answer them in the dedicated QA, right? So let's assume a scenario that we were talking about, that your business has given you a task. Maybe your manager has given you a task to come up with some model, maybe prediction model, maybe fraudulent transaction prediction model, and you have 6 months for preparing that particular model. Now you go, you prepare your data, you identify the sources, you do the feature engineering, you have all the data prepped, you have some models experimented, you have done kind of a bit of permutation combination for different models which fit well, and then you have passed that to the machine learning engineer. They have done their bit of having these models prepared for deployment, and you just turn out to your manager and say that, okay, I am done with this model, and already 5 months have elapsed. Now your manager tells you that, okay, as of now, we see that the data that was provided to you has changed. The features that we were working on have changed. The requirements and the business alignment has changed, right? So whatever you did for 5 months or 6 months, right, all of that has gone in vain, and you will need to start from scratch, just to realize that in the next 4 months, again, the same scenario is going to happen likely, wherein the data you were working on is now obsolete, is not referenceable, and you need something new, or you may need to have some more feature engineering done, or maybe you need to tweak or refine your features and clean your data, or maybe have your data modified in accordance to uh, the new business requirements which have been shared, right? So that is where it calls for operational excellence, and we will see in this session how we can achieve that. Then there may be multiple teams. Already we have identified that there are different stakeholders like data engineers who are coming towards the beginning of the cycle, as well as helping the data scientists with the platform needs, helping the machine learning engineers with the platform automation, etc. And each of these teams not necessarily will be using the same set of tools. So some people will have affinity towards some particular set of tools, right? You will have teams which are biased because of they have experience with the tool, or maybe the tool is really handy, or maybe they have done a lot of projects using those tools. So they have some affinity, or they have some biasness towards the tools, and you may not have a unified tool set to support these requirements, right? And then you are also trying to build multiple models. So there are multiple teams who are using multiple tools, and they essentially are going to build multiple models, but all of those models are going to solve some business need, and all of those models may be required to solve some particular use case as well, but these models are getting solved in sub teams, right? So that is where you need some operationalization in the framework, so that you can have some standardization done, you can have some reusability done, you can reuse the things which were developed earlier, or maybe you can reproduce the things, and you can have some checkpoints, you can have some governance in place. If at all someone says that I need to check what happened with this particular model, or maybe we deployed this model in production, and it's the version V1. Now, how it compares with the new model which you are coming up with, the version V2. So all of those things are essentially going to give you a hard time if you don't have operationalization in the framework, right?
Hello,
Then
sir. Hello,
we
Anmol,
see
sir.
that there are.
I would like to just let you know that a few people are not able to see your screen. So,
Okay.
would you please like to reshare your screen?
I
Because a
think, yeah,
lot of people.
whosoever is viewing, right, in the Zoom, there is a button on the top which is called View. Have speaker view along with screen ticked on that. Okay. So it's called side by side speaker screen view. That should be solving your issue. Okay. Should I continue?
Yes, you can continue.
Okay, thanks. Yep. And we see that sometimes it is very hard to manage models which have a lot of kind of data, right? There are large backlogs of models that are to be published, or maybe they are queued because they need to go in some particular sequence. And there's no standard way to audit, monitor, test, or even maintain the models from a future perspective. So there's a big question on the life cycle and governance constructs. Okay. We just see that according to Google Trends, the MLOps term has got a lot of traction. Okay. And since 2004, you see that it has grown a lot. Okay. So the interest in this field is growing just because there is need of MLOps in the field, right? So what's required for AI ML projects? And whatever we are going to talk about hold true for even AI projects, right? So it's not very much restricted to just ML projects. We are even talking about AI projects here. That is why I've mentioned ML and AI projects. So ML AI projects generally require cloud native platforms, right? Because there's a lot of compute to be done. There is requirement of containerized workloads so that you can have the same environment or the same set of configuration persisted across different attempts that you do in different environments across your organization. And you have also sometimes a requirement of serverless technology or integration with some cloud technologies, wherein you will be hitting some cloud functions, maybe PubSub or maybe Lambda functions in AWS, whichever you can relate to. So serverless technology is also required for having some of the tasks delivered, right? And then you see that there is many a time specialized hardware which is required. And essentially, you will see that some of the models are working good with GPU, some of the models are working good with CPU. And while training the models or while prepping for the model throughout the ML pipeline, you may require different node configuration for each of the tasks that you are performing. So data prep, if it has to be automated, will be having its own configuration requirements. Data cleaning, feature preparation, and feature engineering will have its own set of requirements. You will have machine learning model deployment, serving, etc. have their own deployment requirements from a node configuration standpoint. And then there is a hard requirement of having integration with the data stores, with the big data platforms, with the tools like Hive, Pig, Spark, Hadoop, etc. Right. So all in all, we get a common theme from all of these things which have been put on the screen. And that theme is machine learning and AI are very close to cloud, right? They are very much reliant on cloud. And I would, it is hard to imagine any AI ML pipeline in today's scenario which is not utilizing some of the cloud constructs or features or products, right? So more or less, you will have majority of them utilizing the cloud technology at some point of time. Okay. So let's get into what is MLOps. So essentially, MLOps is just the tip of the iceberg, right? So you see MLOps is placed at the top here. But essentially, what comes as, or maybe what serves as pillars to the MLOps, there are three essential domains or pillars. One is DevOps, which is the, you can say, bottommost pillar, right? Or the bottommost stack item that you need to focus on. If you have DevOps sorted, you will be having a lot of you will see that your MLOps thing, or you will be better positioned to be successful in your MLOps journey, right? Why DevOps? Because essentially you are discussing about continuous integration, wherein you are having new things getting launched, or new feature or new code getting introduced, or maybe new configuration getting introduced. And then that new configuration is essentially uh, new configuration is essentially going to get tested because of continuous integration. Once that is tested and it has passed all your test cases, maybe you have unit testing, maybe you have integration testing, behavior driven testing, all of those things you can take care of. Once that testing has been done, you are good to have your things deployed or delivered using continuous delivery, continuous deployment. So DevOps is really a very strong construct and requirement for achieving MLOps, because of which you will be having most of your automation uh, requirements handled for CI/CD. Then comes the data automation portion, wherein you are essentially going to have periodic collection of data, right? You may be running jobs, you may be having stream processing for your data, you may even have serverless or event driven triggers for your data gathering collection needs. You may have some big data feature store, or you may have some big data jobs for processing your data. You may be utilizing data lake, etc. And the most essential part of this, which is very much required for MLOps, is from a data operations and data automation point of view, you need the data and model versioning to be done, and you need some checkpoints to refer to. So all of that is something which comes as part of the data automation stack. Then comes the platform automation stack, and platform automation is, we can say, the pillar which is required to have your platform or infrastructure supported to enable the machine learning pipelines, to enable the machine learning automation. So once you have the data flow automated, you have achieved the data processing nirvana or something. You essentially have this platform wherein you will be required to have different hardware supported, different node types, different virtual machines. Maybe you want to go with Kubernetes. Maybe you want to have some IO done with respect to your storage buckets for data lake. Maybe you want to have some production endpoints generated for your ML pipelines for serving those. So all of those things essentially
Hello,
are covered
Anmol.
from a, yeah.
Yeah, you shared a screen now. Like you are on the
Yep.
first page, or you're still on the first page now. Yeah.
No, I'm not on the first page.
Because now, yeah, it's not visible for everyone.
Okay, let me start resharing. What do you see? A pyramid?
Yeah. Yes. Now it's visible.
Okay. I'm not sure what happened. Okay, thanks for pointing this out. And
yes,
okay, yeah. So what we missed, if you this, so we missed this particular trend. Okay, we missed these bullets which I was talking about, and essentially these technologies which are required for AI/ML, right? And then we are currently talking about the pyramid. Okay. So I hope you followed the audio though, right? If not the video. So then comes the MLOps, which is essentially the process of automating your machine learning using DevOps methodologies. So DevOps is a behavior, right? DevOps is a methodology. Likewise, you have machine learning operationalization, also a methodology or a behavior. Essentially, you are building machine learning models which are following some standard practices and which are leveraging the DevOps practices. And essentially, you have operational excellence, massive scaling, standardization, streamlining of data pipelines, and again, some problem.
Hello, Anmol. Sorry for interrupting, but
Mm-hmm.
it's again we are seeing the blue screen again.
Okay, not sure why this is happening. Give me a second, please. Is it okay now?
It's not visible.
Is it okay now?
Yeah, now we can see the pyramid. Yeah.
Okay. You see the
Yeah,
screen
now.
moving, right?
Yes. Now
Okay.
it's
Okay.
perfect.
Yeah. Okay. Thanks. So essentially, MLOps is going to help you with standardization of your machine learning pipelines, streamlining your data science workflows or ML workflows, right? And you are going to have your governance, your project lifecycle management, operational excellence, all of them kind of guaranteed or sort of addressed, right? So in short, you need four things which will help you with MLOps, right? First thing is that you need to have an ML ops feedback loop structured in a manner which makes sense and which is very much aligned to technical as well as business requirements, right? So the feedback loop includes creation and retraining models with reusable ML pipelines. So you create a model just once and that's not enough, right? You will need to have the model recreated because the data will keep on changing, your requirements will keep on changing, and the term we use in the machine learning terminology is something called as degrading of data or decaying of data, right? So essentially you will have that your data is decaying, it's not relevant now, or maybe in a few days or few months time or few weeks time it is not relevant, so you will need to retrain the models, but still you will need to hold the reference to the other models, what the other models perform. So you will need some sort of checkpointing, some sort of versioning for your models, right? And this is where you can have some aspects which will be reused as well while building the models. So you need to have this thing solved first, which is creation, training, retraining of models with reusable ML pipelines. So the first focus pillar in the feedback loop is this. The second one is deploying and versioning of ML models. So you see that you will be having your continuous delivery for ML models done. And it is very similar to the continuous delivery of software, but the only difference is software is more or less static. And software is more or less static, and machine learning is dynamic because of the nature of data, right? Then you have something called audit ML models and artifacts. Essentially, this is from an auditing perspective, from a governance perspective, you will need to have some artifacts monitored, audit the ML pipelines monitored, right, and audited. And you will also have to look at what exactly is changing in your data so that you can adapt and you can iterate on your models to fit the needs, right? Both the business and technical needs. So from a stakeholder perspective, right, you have different parties as part of MLOps. The first one is essentially the business stakeholder, which should be involved pretty much early in the planning phases. You should be getting inputs as with respect to what one needs to deploy, what are the business requirements, what features one need to stress on. And the focus should also be on how the model should be deployed, right? Because model either can be deployed in a real-time fashion or can be deployed in a embedded fashion, right? So more or less, these are two broad categories of how you have the models deployed. So you will need to have a clear alignment with business, whether they want real-time predictions to be done or whether they want embedded predictions which happen over a batch, right? So all of those things actually help you in having the feature engineering and preparation done. You have data scientists which are acting on all of these things with respect to data preparation, model training, model experimentation, having a playground and permutation combinations of different models tested out. And you have data engineers which support the requirements from a platform perspective and even give you the way to have data ingestion done. Then you have some DevOps people, you have data engineers, you have machine learning engineers, which are essentially working together to solve machine learning code, the deployment, the serving of the code, monitoring of that, CI/CD perspective, containerization of that particular code, and evaluation from a drift perspective, from an auditing perspective. So all of these stakeholders have to work together. So essentially, if you see, it's very much the flow which we saw in the feedback loop, and it aligns from a stakeholder management point of view as well. So a high level MLOps workflow which will look like this. So you will have your data ingested, it will be kind of transformed. So this portion involves involvement of the data engineers, then it is followed by the data scientist. You have the data preparation done, which is given to the ML engineers. You will have the model build, you will have the optimizations done. You have the model served, and essentially it is followed by logging, monitoring, and the iterative loop for the audit, etc., and fine tune. So we now know that what MLOps is from a broader perspective. So how we can actually realize is something that is interesting, right? So till now we have covered some theoretical portion. Now on we will cover some theory of Airflow, which will be followed by a demo. So essentially, what is Airflow? Airflow is an orchestrator, and why orchestrator is needed is because all of these phases in the MLOps architecture or workflow which we saw, these phases are to be operationalized, right? These phases are to be orchestrated. Each of these steps have something to pass on to the next step, or maybe refer something from the previous step, right? So all of these phases are connected. There needs to be exchange of information. There needs to be some coordination between these tasks, and because of that only you will be able to have end-to-end streamlining of your ML pipelines. So Airflow is an orchestration tool. There are other tools in the market as well which are equally good, but Airflow being one of the oldest and one of the most reliable, right? Because it is a very mature Apache project. It is something which many people do consider when having data operations or orchestration of data pipelines and ML pipelines, right? So you have other tools like Kubeflow, MLflow, etc., Lugi, Prefect, which can be utilized as well. All of these tools have their own pros and cons, right? So Airflow is an open source tool, and it's used for developing and scheduling monitored batch-oriented workflows. Okay. Again, the issue is persisting, is it?
Yeah, we can see again the blue screen. Yeah. Oh yeah, now it's fine.
Okay. Yeah, so it's like I didn't do anything. So like I didn't go to the next bullet point, right? Because I was discussing about the first only. So yeah. So I'll cover this TensorFlow Airflow towards the end, right? So it's a Python first. It's a Python first framework and supports parameterization of Jinja using Jinja templates as well. So essentially, you can write your pipelines supporting through the Python code, and essentially all of those things can be managed through Python code all in all. And you can even have the sequentialization, etc., done. And just to stress on, this is something which is there for batch-oriented workflows only, right? So streaming, etc., are not the use cases. Then there is a concept called DAG, which is directed acyclic graph. What this means is each of the step essentially. Yeah. So what is a pipeline here? Okay. So pipeline here is the combination of the steps which we saw earlier. These steps are essentially these steps are essentially your data cleaning process, data ingestion, followed by transformation, going to kind of model building, and then optimization of the model, then serving the model, and followed by all the monitoring, auditing, and CI/CD kind of aspects, right? So a pipeline is a combination of all these steps linked together. So this is what you are having. So you see the arrow going from data cleansing to data ingestion, etc. And this is kind of going like this, and then you have model. The model is served, and then you have the monitoring done. So pipeline is essentially a sequence of steps which are followed to serve your ML model, starting from the exploratory phase to the productioning and production phase, and then followed by maintenance, and it goes on in loop then, right? Okay, yeah. So So coming to DAG workflow, DAG is essentially a directed acyclic graph, and that is the foundational concept of Airflow. What DAG serves the purpose of is, and we will see this in the demo. So say you have task one, which is data cleaning, and now you want to do feature engineering, which is the second task, right? So inputs from task one should be passed to task two, right? So this means it is directed. So task one is to be followed by task two, which means it has some direction, right? So one node has another node which is following it. Acyclic means you cannot have a cyclic loop. So task two cannot go back to task one, right? So essentially, if data cleaning is happening and you are passing the data to the data preparation phase, you cannot have the data preparation phase go back to data cleaning, right? So input of data preparation will not be given to the data cleaning phase. So that's acyclic, right? Which means you don't have any cycles between these nodes, okay? So directed means you have vertices which are directed. Acyclic means it is not cyclic, and graph means this is a group of nodes which have some vertices, and these have directions which are not acyclic, right? Which are acyclic, right? So this is what a DAG is, and we essentially can have all the flow steps which we just saw represented using Python as code, and all of those things can be called as functions using Python, or maybe using the syntax of Airflow, and that is where you will get a DAG formed, and we will see that in the demo session. All right. This is extensible with operators, so you have many integrations, and essentially it has many integrations, and essentially it can be integrated with third parties even. So if you want to have BigQuery connector, you want to have Cloud SQL connector, you want to have MySQL, you want to have Hive, you want to have any DBT or any other connectors, right? Even with Kubernetes, GKE, etc., S3, EMR, MapReduce, right? All of those connectors are available, Presto, etc. So it's extensible with third-party tools. And you have task dependency management. You have parallel execution. So if there are tasks which can be executed in parallel, maybe there are multiple data cleaning jobs which you are performing, or maybe there are data cleaning jobs followed by a grouping of the data, or maybe chaining of the data, or maybe clubbing the data together. You may have multiple jobs for that, and you may have multiple data sources. So all of those tasks which are capable of being performed parallelly will be executed parallelly as well. So that is the beauty of this framework. And if at all due to some issue you are not able to have your task execute properly, there are retry and notification mechanisms as well. So you will get the proper alerting, monitoring, logging, reporting of these things done. So if say during execution of task you had some network connectivity issue with your data store because of which the task failed, right? It will report that it failed the task, and depending on what configuration you have provided for retries, it will be able to retry the task, right? And as many times as you specify, it will be able to retry the task. And unless the current task is successful, task two will not start getting executed, right? So if task one is unsuccessful and is in retry loop, since task two is dependent on task one because of that directed vertex that we have, we will not have task two execution started, right? So this is essentially wherein if at all anything is breaking in your pipeline, you will not have the subsequent phases execute, and you will be stuck on that particular phase, which will require your attention. And once you fix it, it will automatically start the execution of the next phases. So talking in terms of the Airflow components, there are essentially 4 Airflow components, or 4 critical infrastructure components from Airflow perspective. One is the Airflow web server, one is Airflow scheduler, one is the executor, and one is metadata store, right? So what these components mean, let's understand them. And all of these are something which we will be visualizing in the demo. So you will get to see all of these components, and we will make references back to all of these things which we are discussing. So Airflow web server is essentially a web UI. Okay, you have the DAGs, or the directed acyclic graphs, which you are writing in Python, available on the UI, and there is provision to go about having those DAGs run. You can schedule the run of those DAGs. So essentially treat it as something which is a dashboard which is being offered to you, through which you can have these pipelines executed through DAGs. You can have them monitored. You can check the logs. You can have these orchestrated. You can go and you can have some notifications laid out. You can form connections with the databases, external databases, maybe by passing the password, username, etc., the connection ID. And all of these things are also possible through the management APIs of Airflow. So Airflow has a rich API. You can utilize that for interacting with the web server components, or you can use the UI, or there is even CLI which you can utilize, right? So web server is essentially the management plane you can consider, which is showing you these things. So essentially, it's the core component of the management plane or master plane. Scheduler is essentially a component which is used to schedule these workflows or pipelines, right? So suppose you have two tasks. One is data cleaning, and that is followed by data preparation. Now, data cleaning is the first task that should be getting executed. In order to get executed, it should be scheduled first to some infrastructure, right? It may be a virtual machine on which it is getting scheduled. It may be a Kubernetes pod on which it is getting scheduled. So essentially, scheduler is actually taking care of having your tasks or the steps scheduled, right? So task 1 is getting scheduled, it is getting executed. So task 2 will not get executed unless task 1 has successfully executed. That is something we learned, right? And there are mechanisms through which we can say that task 2 will remain in some queue unless task 1 gets successfully executed, right? So queuing mechanism is also something which is present, and that is part of a few executors that are part of Airflow. So executor is essentially the component which helps you execute these tasks, right? So first we have web server, which is offering us UI management APIs to have these tasks reported and registered in Airflow. And then you have scheduler, which is going to actually schedule these tasks when these tasks should be kind of are ready to execute. So it is the scheduler which takes care of that, right? And you can even provide some cron schedule. You can provide some presets based on which you want to have the tasks executed, right? So you can say that I want my task to start execution only at 2 a.m. In the early morning, and I don't want it to be running in the evening or afternoon time, right? So you can decide on when your task should run, what's the silence period for your business, and then you can kind of have accordingly the tasks run, right? Then there is something called as Airflow Executor, which essentially gives you the power of having these tasks literally executed. So you will have these tasks either executed on virtual machines or Kubernetes, or these tasks executed using some kind of third-party integrations. So executor takes care of having these tasks properly initiated on the target system, maybe virtual machine or maybe pods. And then from there, you have these integrations getting triggered. So again, execution may be a queue-based execution, or it may be just like a task is getting assigned and you have a new pod getting spun up, and that pod is executing your workflow step, right? And then you have a metadata meta store or database, which essentially literally means what it is named after. So it is storing the metadata of all these executions that are happening, of all the management that is going on with the cluster, the web UI, whatever updates it is getting, all of them are getting stored as metadata. Likewise, scheduler will say that, okay, I have scheduled this job. Now, whether it is successful or whether it has got failed is something which will be reported back to the meta store. So this is essentially a central database, a metadata database, which you can maintain, right? And there are different options for these metadata stores as well. So you can have Postgre, you can have SQL. So there are different options to support this metadata store as well. And coming to executors, which is going to be a critical thing before we get on to what is there in Kubernetes and our demo. So there are majorly 4 executors, but there are many more as well. One is sequential executor, which will ensure that you have your jobs sequentially executed So no parallelism or no concurrency is there, and this is executed in a local environment, right? So if you are running Airflow on your laptop, you have these tasks executed sequentially one after the other. Even though the tasks are of parallel nature, some of the tasks may be executed in parallel, but your machine will not allow, because you have selected sequential executor. So you will have a sequential execution of the tasks in your ML pipeline, right? Then you have local. Local is essentially a variation of sequential, but this is something which can be made parallel, right? So it runs on local, but it has the parallelism feature, right? Then there is Celery executor. For the people who are from Python background, they would know that Celery is a asynchronous task queue management system, and essentially where it is getting leveraged is to have production based ML pipelines or Airflow tasks kind of orchestrated. So you have essentially a queuing system in between, like RabbitMQ or Redis, through which the tasks are queued, and essentially you have target worker nodes, and whichever worker node is adhering to the configuration required for the task, and whichever worker node has the capacity to run the task will be chosen, and the task will get scheduled from the queue on that particular node, right? And once that task execution is done, whatever is the next task will get executed. If you have multiple nodes, you can scale out, you can horizontally scale these nodes. So if you have multiple nodes, you can go about having multiple tasks executed in parallel. So you have the parallelism, you have the concurrency settings, and that is why it is a production grade offering or a production grade executor, right? Then comes Kubernetes, which is fairly recent in this ecosystem, and that is again production grade, and it also has a variation of having Celery run on top of Kubernetes. So you can leverage the Celery, the main kind of benefits of Celery, and the benefits of Kubernetes from a scaling perspective as well, right? So essentially, from a Kubernetes executor standpoint, what we need to consider is that all the other things which we saw, sequential, local, Celery, these were running on virtual machines or maybe on machines or nodes. But Kubernetes is essentially where your task will run in pods. Okay, so you will have pods created in Kubernetes on which your task will be running. And then if at all you choose Celery, you will have these additional queuing components which will be coming in picture. Again, those will be deployed as pods, okay? But you will have the same mechanism of asynchronous task queuing, etc., and distribution of tasks respected. So it will bring you the power of Kubernetes. It will bring you the power of Celery. It's an option, okay? There is an option to go with Kubernetes, but not with Celery as well, right? So all of those things are essentially possible, right? Yeah, I'll be sharing the presentation and material. So yeah, and someone is asking about cron scheduler. So essentially, cron scheduler is something which you can think of as a traditional thing to go about scheduling the tasks. Airflow or orchestration frameworks are giving you a lot of power on top of what a cron scheduler has to give, right? So cron scheduler will just be able to have your tasks run according to some cron job or a cron job preset or any schedule. But Airflow is giving you management capabilities, data sharing capabilities, integration capabilities, retry mechanism, dependency mechanism, dependency tracking, and all of those things that we discussed in the introduction of Airflow, right? So it's very, very advanced than cron schedulers, right? So don't mix the concepts. Yeah, the context is that it starts with cron scheduling as an idea, but then it goes on and builds on top of it, and it has really matured in that space, right? Now, coming to Kubernetes, there are three essential ways of how you can have Airflow running on Kubernetes. One is through the Kubernetes executor, which we saw, wherein you also have an option of having Kubernetes along with Celery running. But then there are two more options in KEDA, which is Kubernetes event-driven auto-scaling platform. That is one of the most kind of recent and stable kind of, I can say, releases or features of Airflow. So we'll go through these one by one. So first thing is the Kubernetes pod operator. The Kubernetes pod operator essentially is different from Kubernetes executor in a way that in Kubernetes pod operator, you will have control over the machine the container images of each of the tasks, right? So you can have each of the tasks, like data cleansing, can have its own container image, can have its own hardware requirements specified, node pools specified, labels, selectors, taints, tolerations, etc. specified. So all the Kubernetes constructs, all the Kubernetes API constructs from a scheduling perspective are applicable to each of the tasks, and you can have each of these tasks run in different containers using different images, using different configurations. You may require one task to run GPU, one task to run CPU. All of those things is possible using the pod operator. How it differs with executor is that executor just follows one standard container image, right? So it's a beefy image that you will create that will have Airflow, that will have all the dependencies that you have for Python and all the dependencies you have to start integrations with the other platforms. Maybe say you are using BigQuery, so you will need to have cloud support. So you will need to have the cloud library or SDK for Python also installed as pip requirement. Maybe if you are using scikit-learn, you will have sklearn and pandas, etc., to be downloaded, and it will be a single image, and that image essentially will be getting every time up as in form of a pod, and you will have the task run on the using the same container image essentially, but these will be like different pods that you will be running, right? Whereas in Kubernetes pod operator, you are getting pod level kind of control, wherein for each task you can have different definition for the pod, right? So it differs in this way. So executor is like a standard configuration you follow, and all the tasks get executed in the pod that is there. Whereas in Kubernetes pod, you will have individual pods created, and that is where you can kind of have this different configurations managed. And then comes the Kubernetes event-driven auto-scaling feature, wherein you have this is essentially meant for celery execution. Okay, so Kubernetes event-driven autoscaler is a platform that helps you auto-scale Kubernetes workloads and deployments based on some custom metrics, right? Or events or external metrics or events. Like if you want to auto-scale your workloads on based on some specific metrics like number of DB connections or number of say the lag in the queue, right? All of those things can be done using Kubernetes event-driven autoscaler, and this is where Airflow introduced this option for having celery executor, because based on the overhead of requests, based on the tasks that are there, right, it will be able to leverage the elastic scaling capability of Kubernetes and still have celery workers run on that, right? So this is one of the recent additions that are there, and essentially it is running as a custom resource definition. For the people who are not aware with custom resource definition, it is an advanced construct in Kubernetes, and there is an object called scaled object with a scaler as a resource, which is used in CRD. So it's just a custom definition of one of the resources which the Airflow team has defined, so that these can be run in Kubernetes in the manner other deployments work, and it can be auto-scaled using the KEDA feature, right? So I see like a question here: what is the difference of running Airflow with Docker with Kubernetes? So Kubernetes is essentially giving you orchestration capabilities, whereas Docker, you may utilize Docker Compose, etc. But again, those are like old platforms, and you will not be able to leverage the auto scaling capabilities, etc. The hardware the configuration for hardware that you want to perform based on different workloads. So all of these are something which you can get from an orchestrator framework, and this is where like Kubernetes outshine, right? And then there is another question: how is DAG fitting in this part of the process? How is it necessary? So this is something which we will see in demo. So maybe like 2 more minutes and we get to the demo, right? So these are 3 ways of how Airflow can have the pipelines run on Kubernetes. And from a Kubernetes executor perspective, this is the high level architecture diagram of how it looks like. So you have these components which we explained: web server, which is supporting the UI, you have scheduler, you have Kubernetes executor, and you have the Airflow configuration, which is essentially powering the behavior of how Airflow works. You have these DAGs, which are nothing but Python code pieces or snippets that you are pushing, and these are getting pushed to the web server, because of which they are having these configurations loaded and getting scheduled, and these are getting scheduled on the Kubernetes executor. The Kubernetes executor is then going to have the pods created based on the template, the common template, the common container image that is there. And these workloads, each of these pods will be capable of running the tasks, right? Again, there is some problem with screen, is it?
No,
Okay.
it's visible.
Okay, thanks. You see the demo page, is it?
No, demo pages. Yeah, it's the same Kubernetes executor.
Okay.
Yeah, Kubernetes
Okay.
executor. Yeah.
Visible, right?
Yes, yes.
Okay, yeah. So now we come to demo portion, right? So what we will do is we will create a Kubernetes cluster. For this particular demo, I have created Kubernetes cluster in GKE, which is Google Kubernetes Engine, which is running essentially Kubernetes as a managed service on top of Google Cloud Platform, right? So what we are going to do is we already have a Kubernetes cluster up and running, and we will fire commands against that. If at all you have a Kubernetes cluster with you, you can also follow along. The Kubernetes cluster doesn't need to necessarily be on a cloud platform. You can even have it on Minikube or your local using Docker desktop, or if you are using kind Kubernetes in Docker, you can use that as well. So there's no restriction as well. You just require a Kubernetes cluster with some capacity so that you can have the workflow scheduled on it, right? So now what we are going to do is I'll bring up my terminal, right? And we are going to have the Airflow thing deployed, the Airflow component deployed using Helm chart. Okay, so what I have done is I have a Kubernetes cluster which is called Airflow Kubernetes 00. Okay, I believe it is visible, and that cluster is having 3 nodes as of now. Okay, these are the worker nodes on which we will be having our Airflow specific components scheduled, right? Now, what we do is first thing is we utilize Helm. Okay, so Helm is a wrapper on top of the Kubernetes, I can say API that is giving you functionality of maintaining your Kubernetes releases. And essentially, it gives you capability of managing these releases in a very intuitive manner, and you can perform rollbacks, you can have maintenance done, you can track the releases, you can have registries added, and essentially you can utilize existing uh, workloads. Maybe you want to deploy Redis, so there's no need to go about having Redis created by you. Essentially, you will have to go and have you can pull the Redis image and related artifacts or chart, as we call it in Helm, uh, from the Helm repository or registry, and then you will be able to deploy it on Kubernetes. So all in all, it gives you templating capabilities, right? So you can have boilerplates created or templates created using the mustache syntax of Golang. We call it the Golang templating engine, which is supporting Helm. And then once you have created that, you can bundle those resources or the Kubernetes manifest files in form of something called as chart, right? Now, once you have that chart created, you can deploy it in public over some registry, or you can keep it in local registry as well. Once you have that created, you call it as a chart bundle or a package solution, and that is where you have it called as a package management solution for Kubernetes, right? So it is giving you templating, it is giving you release management, it is giving you package management. Uh, each of the packages can be, or charts can be versioned, right? So this is where the actual beauty of package management is coming into picture. Someone has a question. What is the difference between Ansible and Helm and IAC by Helm? So these are two things, right? Helm is essentially there to have your Kubernetes kind of manifest or configuration, which are essentially from a Kubernetes native standpoint, these are applications, right? So you have these applications getting bundled, the Kubernetes applications getting bundled, whereas Ansible is something which is not specific to Kubernetes as such. It can be applied for configuration management, etc., for other components as well, even virtual machines or configuration for some other OS as well. So you can have that for it. And how it differs from IAC is You have certainly Terraform provider for Helm, wherein through Terraform or infrastructure as code, you can manage Helm. But essentially, when it comes to Helm, it is there to have package management solution for the applications that you want to deploy on Kubernetes, orchestrated or managed, right? Uh, so it's more on the application side, though people have started providing the Helm providers for Terraform, wherein you can have all of those things managed through IAC, but it's just like you have provided a wrapper, and you are utilizing it through IAC, right? Can Argo CD work in place of Helm? These can work in conjunction, I would say, right? And even like you can have Argo CD play the role of orchestrator instead of Airflow. So all of those combinations are possible, right? So what we do as of now is we add this repository of Airflow, which is having the Airflow chart, which means it is a bundled Kubernetes configuration. There are some alternatives out there which just provides you templating capabilities like customize, etc. So we go and we already have this repo added. So essentially it just misses that it is there. And just to list what all repos are there, we will utilize Helm repo command. This will give us the list of charts that are already there on our system, which we can deploy, right? Where does this repo link comes from is the question. So these links, earlier there used to be a central registry wherein all of these were getting pushed. But then since like last 2 years or so, we have these maintained by the maintainers of the products. So you can find these repos in the GitHub or maybe the registries that are maintained by the maintainers. Okay. Earlier it used to be on something called as Helm Hub. Now people can have these hosted on Chart Museum, even your kind of CI/CD registry, like even you can have GitLab registry maintain this, or maybe if you are using something on the lines of Nexus, etc., as Artifact Hub, you can have those there. And even Helm charts are now possible to be hosted in Docker registry. So that support has also been introduced. So you can have these charts hosted. And where to get the link to these charts for Airflow, this is the link which you see, the command which you are seeing. But for different providers and different systems, you will have different repositories, because those will be the repositories maintained by the maintainers of these products, right? So we essentially have many charts here, out of which we are going to utilize the Airflow chart. Now what we do is we first have a thing called Helm install command. Okay, this is essentially telling that I want to have Helm installed. And upgrade install essentially means that I want to install if it is not present in the machine. If it is present, then I want to upgrade the chart, right? It is giving the name to the chart, which is Airflow. Then it is providing the name to the chart repo, okay, Apache Airflow. And in that we have the Airflow chart. And then the Kubernetes namespace in which we want to have this chart created, debug mode to just trace what is happening in the command as we move and we make progress, and create namespace. If this Kubernetes namespace doesn't exist, then I'll have this created by the Helm utility, right? So this will take 2-3 minutes and it will create deployments, stateful sets, etc. So let's do one thing. We split the screen and we start watching what is getting created, right? So, and I'll increase the font size. Okay. Or let me do one thing. Instead of pods, I'll do all. Right, so you will see the deployment, replica set, etc. come up. And this is going to take like 2-3 minutes. So it will be creating deployments. It will be creating the necessary stateful set. It will be having these all these components which are required from an execution point of view created in Kubernetes. So secrets, RBAC, services, and anything that you can think of, right? Those are the things which will get created. So you see on the top, you are having these things created. And till now, it has been kind of working on creating some secrets, etc. Now you see that it has popped up with deployments. It has popped up with replica set, stateful set. So it will take like 2-3 minutes before all of this gets concluded. And once it has succeeded, when it succeeds executing all of this, you will see that it will give you some instructions as to how you can go forward with the Helm chart, right? For Windows other than WSL2, there's a question, okay. What other options for setting up containerization, low storage option within VS Code? Yeah, so you will need the subsystem for Linux, I would say. In this case, you can try out Docker desktop on Windows. That again will be dependent on virtualization. But yeah, to the extent I know, you will be requiring the subsystem, Linux subsystem. Okay, in the background, what we will do is we will see what is happening in our Kubernetes cluster, right? So we will go to a Kubernetes cluster and we will see the workloads, okay? And these workloads are, we will just see the workloads corresponding to the Airflow namespace, okay? So you see that these components are getting created. You have Postgre, you have Redis, you have the Airflow migration job, which is run to have the Airflow migration specific like kind of data migration with respect to the metadata that is there conducted. You have the scheduler, you have statsg. You can even have components like Redis, etc., which is showing up here, right? So all of these things are possible using the Helm chart, right? So all of that is getting created, and by default, you will have Airflow come up with celery worker or celery executor, and you can have the configuration done in the Helm values through which you will be able to have the Helm specific stuff created, right? So what we will do is, I think more or less we have the Helm chart ready, okay? So it mentioned that, okay, this is the message which we got, that Airflow got installed and we have the pods up and running. So what we will do is we'll have something done, okay? What we will do is we will have, we'll have the values shown for the Apache Airflow chart, right? And this is where you actually get to see what all configuration is getting maintained in Airflow. Okay, so this is essentially something called as Airflow CFG or Airflow configuration. This configuration lists down which executor you are working with, what's the security context, right, on Kubernetes, what should be the deployment name, what should be the images with the tags, what should be the image pull policy for all of these components, right? What should be the node selector, etc. So all the Kubernetes things or the configuration which you can think of. Even there is a mechanism to have your private Git repositories directly be fetched, and based on the code, that code that you have provided, you have them fetched, and accordingly you have the workflow executed, right? So this is the configuration. What we are going to do is we have modified a few bits in this particular configuration. So first thing is, instead of celery, we have Kubernetes executor mentioned here as part of the executor, okay? And we have added some extra environment arguments to support our Kubernetes deployments, okay? And those are these. Like I have created some service account, I have created a namespace. This namespace ideally should be screen got stuck again, okay. You have the Kubernetes executor, you have the Kubernetes namespace, etc. So all of these things are essentially something which you can see. So once you have deployed this chart and once you have made the changes, you will be able to go and you will be able to see the Kubernetes services, right? By default, it comes with cluster IP. But what I have done is I have provided, so you see that Kubernetes web server is coming with cluster IP. But for in interest of time, what I have done is I have created another cluster in the background in which I have given the service IP as the load balancer type. So this is where I have this web server getting exposed using this particular public IP. And this is where I see the Airflow UI. Okay. So this is the Airflow UI. You see a set of DAGs. You see the data sets that you are working on. You have some connectors which you can work with, right? You have the DAG job run. You have the logging monitoring information, the data sources, and some admin constructs wherein you can say, I want to have sharing of information using XCOM. So XCOMs is sharing your data across different tasks. You have plugins for having integrations done with third-party platforms. You have connections where you can have connectivity done with, say, SQL, Hive, etc. All right, and you have the docs. So we will be focusing on the DAG. Okay, and from DAG point of view, we will first see an example, and then we will get to the MLOps. I think this demo will take 5 to 10 minutes for the people who think we have gone 10 minutes above. It's going to take like 5 to 10 minutes more. So in the DAG view, we have these different uh, kind of options available, where in grid you see the different tasks that are there, and you see the success status. So if it were to be unsuccessful, say like if this task were to be unsuccessful, uh, you would have seen a red mark here, right? And you have these different uh, kind of options available for denoting the status in which your current task is. So your task may be queued, your task may be failed, your task may be skipped, maybe just scheduled but has not triggered. Maybe it has to retry, maybe it has failed, it has got successful. So all of those things you get through this particular dashboard, right? Then there is a graph view wherein you actually get to see a DAG. Okay. So this is a DAG wherein you have this task one directing to task two. Unless task one is going to execute successfully, task two is not going to have the execution done. And you can have these behaviors skipped or tweaked as well. So task dependency on the upstream or downstream is something which is configurable. So you can say that I will execute task two regardless of whether task one executes successfully or not, or I only want to execute task two if I have the task one executed successfully. Right? You can have calendar schedules done. Okay. And based on the tasks that are there, you can have them. You can have the task kind of looked at, like what was the uh, output of the runs that you performed. Likewise, there are different like task duration, spans, etc., which you can see how much time it took. You have a Gantt chart view with respect to performance and execution time, etc. And you even have the code mentioned here and reflected for each of the tasks or the DAG in itself, right? And you have audit logs, etc. as well. So this is something from an Airflow perspective, how it looks like. What is of interest to us is the ML pipeline, a demo ML pipeline, which is not production ready. So this is very much kind of for demonstration purposes only. But we have this pipeline here, which got executed some time back. We will not be certainly executing this pipeline in this one because it will take more time. But you see that we have the workflow started. We have it followed by data getting loaded on the platform that we want. Then we have the data split. So essentially, it is the example which we have is for the MNES digit classification. So we load the data using the load digit module. We utilize sklearn here. We have data getting split in test set, training set, etc. We have the actual training done using logistic regression in this particular demo, and then we have the prediction done, and then we have the workflow stop. If at all there would have been any cases wherein you would have needed parallel execution of tasks, you would have seen that, okay, split data may have had like multiple tasks beneath, and it may have had 1 to n to 1 mapping, right? Or 1 to n to many mapping. So that is something you can have complex DAGs actually created. Let's jump into the code directly what we have here. So From a code perspective, you have Airflow libraries getting imported, and you have specific operator called Python operator, which we are importing. One thing to understand from a production readiness point of view is, don't try to make Airflow as the system wherein you run your machine learning workloads or you run your training, right? Utilize different extensions that are there. Airflow has extensions with Kubeflow. Airflow has extensions with MLflow. It has extensions with EMR, Spark, Hadoop, etc. Try to have the compute delegated to the systems which are meant for performing some specific job, right? Or some data transformation or some data training. Don't put everything in Bash scripts or Python scripts or SQL scripts and have Airflow executors on Kubernetes or virtual machines run those, right? Have those workers delegate the task to third-party systems, right? So Airflow should be used as an orchestrator tool rather than a training platform in itself, right? Each of the jobs that you are going to schedule, most of them will have some more suitable systems which are very well equipped for performing such those kind of tasks, right? So have Airflow create a task, and that task delegates the task to the third party system which is meant to perform that task in a better manner, right? So what we do is we utilize pandas and sklearn essentially. Okay, so what we are doing is, first thing is we specify the metadata for the DAG, wherein we are saying, okay, the owner is my name. I want to have this DAG started like 2 days back, which means this should be active by the time I have it deployed. And then whether or not I have some cron schedule interval, etc. or not, then I'm specifying my bucket essentially. This is GCP bucket, which I want to maintain. Okay, and here I'll be having my CSV files stored. Okay, these CSV files will be for the data which I am cleaning and the data which I may want to import for building the model. And essentially I'm using pickle to have the model pickled, and the pickled version is also getting stored for the model in our Google Cloud Storage bucket. You may utilize S3, you may utilize some next network file storage. It is up to you how you want to utilize it, right? So what we do is we have something called as, so we already see that we have instantiated the DAG object. Now what we do is we keep on defining functions. Okay, so first thing is we define a function which is a Python callable, and that's not the only approach, right? This is just because we are demonstrating the Python operator, we are discussing about this. What we do is we define the step, and in the step we mention it as a Python operator. This operator could be Spark operator, Hive operator, GCS operator, GKE operator, Kubernetes pod operator, right? Any operator it can be which is suitable to your workload. You define the task ID, which is essentially nothing but how your task shows up in the grid. Okay, so if you just are to see the graph, you will see that this particular task ID is getting shown here. So start workflow is the task ID. It is getting shown here. So it is just an identifier for your particular task. You are saying that in this particular task, I want to call the Python function start workflow. That is why I have defined a Python function here. But we come to more complex steps. So this is like step 1, which we defined. And we have load data, which is the next step, wherein we are essentially loading the MNIST digit data. We are having the data pushed as in form of data frames to the CSV file, and that CSV file I'm pushing to the cloud storage bucket, the GCS cloud storage bucket, for which the logic is here, right? And then we are saying that, okay, we are done with the stage. We have uploaded the data to the GCS bucket, and if the stage executes correctly, we will consider it as successful, and we will assume that our data has got uploaded on GCS, and then we can move to the other phase, right? Here we can provide some keyword arguments or arguments to the function as well. So you see that this particular function, load data function, was getting output path. These are essentially the file names or the paths wherein I am storing the data, and then these CSV files are being read by the GCS client library API, and we are essentially having these blobs pushed to the GCS bucket, right? Then we have data splitting. This is essentially the next step wherein we have the data loaded first. So these two steps are individual, right? These two tasks are individual, and they may execute on different machines depending on the executor that you are using. They may have these they may be run in different pods altogether, and you don't have common storage, right? There is something called as XCOM, which is shareable kind of data or configuration, which you can utilize for sharing some small set of configuration within Airflow between different tasks. But then if you have large files to be shared, right, you certainly need to go with some network file storage system, or you need to go with a blob storage or object storage, right? And this is where I utilize the GCS bucket. You could have utilized anything like S3 or something. So what I'm doing is, since this task is an isolated task in its own, what I'm doing is I'm first pulling the data from the GCS bucket. So I have these data CSV files read, and I am converting them to NumPy. Okay, because now what I want to do is I want to train this. So I do the test train split using the function of the library that I have. I say that I want to have this split into the training data for my data points, and I want to have the this split for the target points as well, the target data points as well. And then I go with again pushing this to S3 or GCS, because for the next task which gets executed, it will again need to load the data from somewhere, right? So what we are treating S3 as a central location wherein we are having all the data processed, right? You could have had a data lake already created from which you could have fetched the data or pulled the data, but in this case we are the ones who are creating the data, and we are the ones who are uploading and pulling the data, right? So this is where you have more arguments applied. Then you have model train. Model train essentially is again pulling the data, and then based on that it is using logistic regression classifier, and then it is just classifying, and in the next step it is just pushing the model to S3, the pickled model to S3 or GCS. Is storage of data to GCS bucket or S3 must, or we can directly use on-premise data store? So that's a good question. If you have connectivity with some data store, given that you are using, say, something like MySQL or BigQuery or some other data store, you need to have a connectivity done, for which you will be using their own dedicated operators, right? So there is no GCS operator as such, or I think there is some S3 operator, but I'm not very sure about GCS. I don't think there is any inbuilt or out of the box GCS operator, because of which instead of a Python operator, if at all you want to use a data store which is on premise, you can go with MySQL operator, or you can go with BigQuery operator, or DBT operator, or Postgre operator, right? That will be able to form direct connectivity with the Postgre, and then you will be able to pull the data in one step, and in the next step you will be able to reutilize the data, given that you are having some exchange between the tasks, right? Or maybe you are having some computation done within the task if the operator supports that, right? So different options are available, but generally these data loading or data pushing are possible through object storage, and if at all you want to have data stores, then you will need to use their respective operators, right? What I used, instead of going with an operator, because there was no readily available operator, I utilized the API, and I could have gone ahead and created functions at the top, but just for demonstration purposes, I'm repeating the code, right? So this can be refactored in a better manner, but essentially you can have the direct API is also consumed, so no one is stopping. The reason why my API invocation is working like this is because I'm already having workload identity federation done with my Kubernetes cluster, right? Which is very much on the lines of if you have used Kube2 IAM in AWS, wherein you have the service account dedicated for your workloads from because of which your workloads running on Kubernetes can directly interact with the services in AWS or GCP. So I'm using that concept of workload identity federation, wherein I am registering service account with the pods which are coming up, right? And because of the permissions that I have given to the service account, the pod is able to, or the service running inside it is able to connect with the GCS storage bucket, right? So it's totally up to you what backend you need to utilize. You can even utilize the on-prem data store. And in the next particular step, the last step, we do the prediction, wherein we are just having the classification score by loading the pickled data and then going about having a score created, right? And that is followed by, like, you can have some email notification done as part of each of these phases, or maybe if you want to have any end kind of logic created. So this is a very minimal one-way data pipeline that we have. And now assume that you were to integrate monitoring, logging, etc. in this, and you were to even mature this based on the MLOps framework that I showed. As in when you have some data getting changed in the source, you will have this pipeline triggered, so you can have sensors that is called the concept of sensors in Airflow, wherein based on some triggers or based on some changes that are happening in any of your environments or any of your sources, you can have a DAG pipeline run. So if at all you have a sensor created wherein it is tapping, if at all the data is getting changed, you will re-trigger the pipeline again from start, wherein you will have these automated flows of splitting the data, retraining the model, etc. worked out. Then you can even go with having a stage added for shadow testing or A/B testing, etc. And that is where these pipelines can be automated in a full circle, so that you can leverage the full MLOps flow, right? So essentially CI/CD, operationalization, governance, uh, all of respecting all of the flows that are there in the ML pipeline, and then going with triggers based on some input sources or some data sources or maybe some events, is the way you can have these things operationalized. And you can even have, for the code constructs, you can have unit testing, integration testing. For the ML constructs, you can have the ML validation and model serving, etc. uh, considered. Triggers and events like, okay, triggers and events like, so there is a concept of sensors essentially in Airflow. So you can have as and when some data source is changing, or as and when you have something which can be acted as a signal to restart your pipeline, right? You can have the Airflow sensors get into picture, and they can go about so it's a special type of operator only, right? So just assume that as and when you have some event getting triggered, and you have the sensor sitting maybe idle, which is polling for that. Yeah. So how data drift can be triggered? Okay. So if at all you have say new columns being added, or you have the data getting changed, right? Or maybe your data that you are ingesting, you have any triggers on that, or maybe you are having some event tracking mechanism because of which you want to signal to your operator that uh, you are waiting on a file, or maybe you are having a time-based polling done, right? All of those can actually act like a trigger. Stop in. Sorry, I didn't get your question. Stop in stream data can be triggered. Sorry, I didn't get your question. If you can retype. Yeah. So so this is where, like, if at all you go to the advanced concepts, you have these things which I don't have in demo as of now, the sensors, but certainly you can go and you can have these things. Streaming data stoppage trigger. Okay. I don't actually get the meaning of this. So maybe like in the QA, we can have a discussion around this. So yeah, more or less, you will have these runs reflected in your graph, and based on that, you will be able to track, you will be able to see the logs of these phases. And that's from a demo perspective, what I wanted to show. So if you want to reach out to me for any of the clarification questions after QA, you can reach out to me on Twitter or LinkedIn. This is my handle, which is shown. Thanks for being such a nice audience, and we are open for QA. Okay, so I see there is a question. Okay, what is DAG process meant for? All right, so essentially DAG process is there to give the task dependency to the system, right? You don't want to go with ML model creation if you don't have the data prepped, right? So DAG is ensuring that whatever data is to be kind of computed, right? Whatever things are meant to be executed in some particular phase, those are getting executed, and only after those are getting executed successfully, you go with the execution of the next phase. And then you can have this data which you produced maybe shared over some file storage, maybe network file storage or object storage or even relational storage, whatever you want to have. Or you can have the variables shared across the task sharing mechanism, which is XCOM in Airflow. because of which the next phase will be able to get the input from the previous phase and it will be able to continue the working, right? So directed acyclic graphs just don't work with Airflow. They also work with other tools like Tecton, like Argo, like GitLab CI, right? Like Lugi. So all of these tools, what I'm mentioning, these like for Git, from a GitLab perspective, you can have your CI/CD pipelines laid out in DAG, right? From an MLOps perspective, you can have MLflow, which is offering very specific ML capabilities, like even model registry is something which it is offering. So all of those things you can cover from MLflow, right? And you can even have integration done with Airflow. So the only thing the DAGs are providing is that you are getting a structure wherein you are having execution done for your ML pipeline in the order it is meant to execute, right? This is what the DAGs are ensuring. Then there is a question for the streaming data storage. I mean, what can be done to set and customize the trigger? Okay, so essentially, as I mentioned, sensors are special operators only. Okay, and you have sensors that work on some poking mechanism, or you have some time-based scheduling. You have some files which it may continuously be polling or kind of reading, and based on that you can have something triggered, right? And you can have your pipelines or the tasks which are waiting on some particular thing triggered, right? So it's more of, if you detect a configuration change, if you detect a file change, if you have some time periodic sync happening, and based on some time interval you want to have something executed, you can go with that. Okay. There is a question, MLflow can be more simpler option, is it? Okay. So there are very good options available, or I would say alternatives available to Airflow. Essentially, Airflow is not specific to data pipelines or ML pipelines. Okay. That is the first thing to be clear on. Airflow is something which is offering you even orchestration of your regular software jobs. Okay. Which may or may not be ML or data jobs, right? And then you may have different pipelines set, different DAGs altogether set for different use cases. So maybe your data prep, etc., is happening in one DAG, and your ML model, etc., is getting trained in another DAG, right? Now this is where MLOps, MLflow also comes into picture. MLflow is essentially a framework which is providing you very much ML orchestration capabilities. Okay, so you have other frameworks also like Flight, like Prefect, etc., Metaflow, which are offering all of these capabilities. Specifically, if we are talking about MLflow, it is also offering you tracking, checkpointing, and kind of record sharing, package management capabilities. But those are very much on the lines of machine learning. If you want something which also works with, say, other workloads, etc., you can go with Airflow. Or if at all you want to utilize best, you want to have best of both the worlds, Airflow has an integrated with MLflow, and that integrator can be used. You can even have Airflow integrated with Kubeflow. So Airflow just orchestrates, and the work is essentially delegated to MLflow, right? So all of those combinations can be used, and it's a very common pattern. MLflow is being used along with Airflow by a lot of enterprises. Should we use GCP to use Kubernetes? Can it be locally done? Okay, so GCP is just because I was having an up and running Kubernetes cluster, a GKE cluster. As I mentioned during the session, you can have Kubernetes cluster even on your local machine powered by Minikube, Docker Desktop. You can have it on AWS using EKS or AKS in Azure Kubernetes service. You can even have it on OpenShift, etc. Your your on-prem databases, data centers, right? You can have Kubernetes clusters anywhere, right? So it's not really dependent on any provider. So no vendor lock-in is there essentially. Okay. Then there was a question around. There was a question towards the beginning, I think, which I said I will answer later, which is TensorFlow versus Airflow, right? So TensorFlow is there for managing your ML code. We saw that Airflow is giving you orchestration capabilities. You just cannot go to production with your ML flow, right? With your ML code, just you need a lot of things to be orchestrated, lot of things to be channelized. Your data should be kept processed model should be created, validated, deployment to be done. So it should be served, it should be monitored, it should be audited, and there should be an iterative feedback loop according to the governance principles of MLOps, right? So TensorFlow is there to create your machine learning code, your model, etc. Whereas Airflow is complementing that and assisting with orchestration of all these things which go into building an ML pipelines. Any other questions anybody has? Please pop up, because my screen was kind of filled with questions or comments. So if I have missed your question, please do pop up it again.
I think everyone's questions is answered.
Okay, great. So thanks everyone. I know there were some technical.
Thanks.
Yeah, so there were some technical glitches in between, some screen sharing issues. Maybe I'm not sure at whose end it was, but I hope you learned something useful. Maybe you can treat it as something to get started with. You got some context, and if you have any questions, please reach out to me over LinkedIn or my Twitter. I'll be happy to answer. And it's not specific to the ML workflow, etc. My specialization is in infrastructure and app modernization. So I myself am not an ML engineer as such, but you can treat me as a data engineer, etc. So if you have any questions for Kubernetes, data engineering, infrastructure, app modernization, API modernization, feel free to reach out to
me. Yes, thanks a lot, Anmol. On behalf of Analytics Vidhya, I would like to thank you for your time and for delivering such a wonderful session. I'm sure our audience found it insightful. So hopeful we are get more sessions with you in the future. Thanks you once again.
Thank you.